G'day guys, Mr. Bell put a video out yesterday going through gradient and length of lines. So I'm just going to take you through about seven problems today. So the idea will be you can pause it, give the problem a go yourself, and then hit resume on the video, and you'll see me go through a worked answer. So our first problem today, calculate the gradient of this line. So in Mr. Bell's video, we will know that the gradient is the rise over the run. So that would be this length over this length here. That would give us a wee right angle triangle. So this length here over this length here. And that was equivalent to the difference in y. So it's y2 minus y1 over the difference in x, x2 minus x1. So our gradient for this will be y2 minus y1. So y2 minus y1, 5 take away negative 1 over, because those are our y values. Because remember they go x, y, x, y, and this is now x2. And x1 is this one. So it's always left to right. So your leftmost point is your x1 and your rightmost point is your x2. So x2 is negative 3 take away negative 6. So in year 9 numeracy, when you were doing all this without a calculator, you know that 5 take away negative is like adding. So we've got 6. And that's going to be divided by negative 3 plus 6. So a negative take away negative is a plus. So negative 3 plus 6 is positive 3. And so we have 2. So the gradient is 2. And there's no units for gradient. So a gradient of 2 there. So give this one here a go. This is your second problem. I want the gradient of this line now. So I've done a wee worked example, so hopefully you can now just use that to help you along here. So gradient, I like to write the formula out just to be really, really careful. That's the rise over run. So y2 minus y1 over x2 minus x1. And so where is that? So this is my x1, this is my y1. Here's my x2, and here's my y2. So 2 minus 0 over, I'm showing full working because I want to make sure I get all the marks. Now if I make an error, it can be tracked. And we have 0 minus negative 3. 0 minus negative 3. So that's going to be 2 over 3. We have a gradient of 2/3. Hopefully you got that. Alright, what Mr. Bell also did is he went through length. So we want the length of this line. So remember, you can create just a right angle triangle off the bat, and it's going to be this distance squared plus this distance squared will give us that distance squared. So if we had a distance D or length L or whatever you want to call it, then D is going to be this length squared. So that would be just like in our gradient, that would be x2 minus x1 squared plus the difference in y, y2 minus y1 squared, and that would all be square rooted. It's just a bit more of a generalized version of Pythagoras' theorem. So this would be x2 y2, and this is x1 y1, and now all you have to do is plug these numbers into the formula. So distance will be x2 minus x1, so 4 take away negative 6 in brackets squared, plus y2 minus y1, 5 take away negative 3, all squared, and then that whole thing is square root. You're probably going to need a calculator for this one. So 4 plus 6, 10 squared, plus 5 plus 3, all squared, which is 8 squared, and that's all square rooted. So that's 100 plus 64, all square rooted, So we're looking at square root 164. You could probably skip a couple of these steps, right? But I just want to make it really obvious what I'm doing. So we're going to go the square root of 164, 12.8. 12.8 units. Not sure what they are. It's just an arbitrary problem. So notice how I write my formula out. I get my formula out, and then I plug in the relevant information. And notice I'm also labeling, all right? I never want to get ahead of myself. I think I can do this without labeling. I label everything I do. If you have me as a teacher, you notice that I label as much stuff as I can, especially if it's trigonometry or measurement based, because order can sometimes matter. In this case, order doesn't matter, because I could create a right angled triangle going this way. Okay, so I could do, and because it's addition of two numbers squared, that order doesn't matter. Okay, so we can usually get away with distance if you make a wee error there. However, this order doesn't matter as well, because in the end you're going to square the difference, so you're always going to get a positive number. So yeah, you're pretty safe with the distance formula. Gradient one, however, if you get this around the wrong way, then you're going to be getting a gradient that would might be pointing in the opposite direction. So let's have a look at this next one. Let's have a look at the length of this line. Give this one a go. Go through that one now. So we want the distance formula, x2 minus x1 squared plus y2 minus y1 squared, and this is all square rooted because we want that length along there, that distance. So I'll label them up. Now my rightmost point gets the 2's, and these would be, if I was going left to right like I was reading a book, these would be the first points I hit, so they get 1's. So let's chuck those numbers in. 7 minus 5 all squared, 7 minus 5 squared, plus negative 5, take away negative 2, all squared, and this is all square rooted. So this is where you might make a mistake. It's just some of this simple numeracy stuff. So we can do this one really easy. 7 minus 5 is 2, 2 squared, plus we've got negative 5 plus 2, so that's going to be negative 3 squared, and this is all square rooted. So I've got 4 plus 9 square rooted, so we're looking at the square root of 13. So let's have a look at that. Square root 13, 3.6. And I'll write units just in case there was units for the length of that line. So there's our first 4 problems. Hopefully you've got the first 4 correct. And I have 3 more here for us to do. So just make sure that's lined up in the camera okay. So sometimes you won't get a line drawn, or you might not get a shape. You might be simply asked, what is the length between these 2 coordinates? And so what I would get you to do is I'd still get you to draw the line. So I look at what's the leftmost. Well, that's going to be leftmost, so that's negative 11, 0. Just do a quick sketch, and then I just have a look, was it going up as I go across, or is it going down as I go across? And it's going down, so we're looking at calculating the length of that line, okay, to negative 15. Okay, it's not important to draw the line so much for length in terms of going up and down, but if you're also asked to find a gradient, you would want to have an intuitive understanding of whether it was a positive line or a negative line. So I just do a quick sketch off in the margins of my book or on a scrap bit of paper, and now I'm going to use the distance formula, x2 minus x1 all squared plus y2 minus y1 all squared, and that's all square rooted. So now I'm plugging in x2 minus x1, 2 minus negative 11 all squared, and y2, that's just negative 15, take away 0 all squared, and I square root that entire thing. So if I was to put this in my calculator, I have square root, and I'm going to do this all in brackets. I could have 2 plus 11 squared 2 plus 11 is 13. So it's 13 squared plus, and that's just 15 squared, isn't it? If I square root all that, I would have 19.8. I had to just chuck that in my calculator because I'm running out of room here. Okay, now back to a gradient problem. So you can find the gradient from -7, -2, and 8, 4. So my leftmost point is this one. That's -7, -2. And am I going up or down? I'm going up if I went to that point. And there's 8, 4. So roughly the line is just going up between those points. It's just kind of what I want to understand. So I should hopefully get, if I do this correctly, I should be getting a positive number. That's why I've drawn this, just to get that kind of, that base understanding. So I know it just removes the possibility of getting an error. So gradient is the difference in y, the rise, over the difference in the run. So x2 minus x1. So these are my 1s and these are my 2s. So y2 is 4, take away -2. Okay, because it's take away, then that number, so -2. So be very careful with that. And then I've got 8 take away -7. So m is in fact equal to 6 over, well that's 8 plus 7, 15. I mean, you can simplify this down, can't you? We can take a factor of 3 out of the top and bottom and call that 3 over 5. Is it positive? It is. So I'm pretty happy with that answer, having a positive 3 over 5. Awesome. And then I'm just going to extend some of this thinking a little bit into something that's aligning more with NCEA Level 2 called Geometry Internal, and it's more of like proofing. So you might get given 3 points and be asked to prove what sort of triangle something is, or you could be asked, given 4 or more points and be asked to prove what sort of shape they are, if it's a square, a rectangle, or a parallelogram or something. So I want to just determine what sort of triangle this is. So what sort of triangles can I have? Well, the first one I could have is an equilateral triangle. I could have that, which would mean I would only need to calculate the lengths of these. If all the lengths between AB, AC, and BC are the same, then I have an equilateral triangle. The other one could be, I could have something like that, scalene, where all 3 sides are different lengths. Equilateral. Scalene, it's the ugly one, scalene, scaly. I remember that from primary school. And you've got isosceles. So that's the 3 triangles it could be. Okay, so I need to find the length AB. So I put a line above it. Some people put a line below. So that means I'm calculating the length of AB. So that distance is going to be x2 minus x1. So 6 minus 5 squared. Y2 minus y1. 8 minus 5 all squared. That's added together because Pythagoras formula and then square rooted. So that distance, well, that's going to be 6 plus 5 is 11 squared plus 3 squared, and then I square root that. So I've got 100 and, I'll just do it perfectly, 11 squared, 121 plus, and that's 9. And then I square root that, 11.4 units. Now my other one is I want AC. Okay, and that distance will be x2 minus x1, 9 minus 5 squared plus -3 take away 5 squared, and that's all square rooted. So I've got 9 plus 5, 14, plus -3 take away 5 is -8, and that's all square rooted. So what I have in there is I actually have 14 squared. I'm just going to add 8 squared, because adding 8 squared or negative 8 squared is the same thing. And then I can square root that, 16.1. So that's 16.1 units. And then the last one, I've done A to B and I've done A to C. So if this was this triangle, A, B, C, I've done that side, I've done AB, and I've done that side, I've done A to C. So I just need to do BC. So BC, the length, so there's an example of lengths being on top or on bottom. So the distance is going to be, we're doing BC now, so 9 minus 6. Right, y2 minus, x2 minus x1, 9 minus 6 squared, plus negative 3 minus 8 squared, and that's all square rooted. I'm just going to double check that one. Yep, yeah, that's right. So 9 minus 6, 3 squared, plus, and that's going to be negative 11 squared. And notice that that's actually going to give us the same value here. So that's going to be all square rooted first. That's going to be 9 plus 121, and then square root that. It is 11.4 units. And so which triangle is this? It's got two lengths are the same. So this length here, BC, and what is it, AB, they are the same. So this is in fact an isosceles triangle. That is an isosceles triangle. The last thing you would probably want to do, and this is going to lead into next lesson a wee bit. Mr. Bell's going to do this for you tomorrow. Is you can actually have a right-angled isosceles triangle. So you can actually have this as a right angle and have these as the same lengths. You can have a right-angled scalene as well. You can have a right angle. Most right-angled triangles have been scalene, right? Your most common one, sorry, it's probably not in your video. Your most common one is 3, 4, 5. Right, scalene, but it's still right-angled, and an isosceles triangle where that's 90 degrees, and both of these are 45. So you might have found that this triangle is in fact an isosceles, but we haven't shown that it's a right angle. And so what we're going to need to do is we're going to need to look at the gradients of that line. So, but for today, we'll leave it there. We do know it is an isosceles, but we don't know if it's a right-angled isosceles or not. But that's just using a bit of that length and distance work. Awesome. There you go, lads.